Hi everyone. I relocated because there was something going on in that room that I was not aware of. Okay, so I think we left off with, wait, hold on. Let me see where I am on the board. This is a new location, so it's kind of hard to see where I am. Okay, I think I understand now. Okay, so, let's just write down the steps of how to do Vsepr again, or like how to draw the molecular geometries again, because this, I really want this reference. So this structure. Two. Steric number 3. Electron pair geometry. I hope that you can see this. I really do. I know this isn't the best chalkboard, but geometry 4 is going to be molecular geometry. Okay, so now that we've got all of these steps down, we're going to start to talk about what exactly you need for the exam again. So I think we left off at me saying hey, you've got to be able to, so now that we're looking at molecular geometry, it's imperative that we look at how many lone pairs we have, and because the lone pairs of our molecule really do matter. And electron pair geometry, it really doesn't matter. It just matters how many steric numbers that you have, and then you get a generic way to draw the electron pair geometry. And then after you get the basic structure of the electron pair geometry, you're going to be able to say, okay, so since we have lone pairs, it's going to be the molecular geometry is just basically a distorted version of the distorted version of electron pair geometry. And the distortion comes from the fact that having multiple bonds or electron pairs or lone pairs is gonna distort it. And so, okay. So now that we're looking at the different kinds of distortions that can occur, this needs to be on your cheat sheet, I think. So now that we're looking at molecular geometry, we need to realize that lone pairs do make a difference. And so what if you have a steric number of 2, right? You're not going to have any lone pairs, and this is just always going to be linear. Steric number 3. So I'm just going to put these in bullet points. And if you have no lone pairs, 0 LP, no lone pairs, equals trigonal linear. Just like when we had the electron pair geometry, when we have electron pair geometry, that's just basically saying we don't have any lone pairs. And so whenever you don't have lone pairs, the molecular geometry is going to be basically the same as the electron pair geometry. But then once you put in one lone pair or electron pair, then the whole structure is bent. Because then that means that of the 3 steric numbers, one of them is going to be from the lone pair. Therefore, you only have really 2 bonds, and so the whole structure is just going to be bent. Okay, and then when you have 4 steric number 4. No lone pairs equals tetrahedral. Again, just like when we had the electron pair geometry. If you have used one lone pair, this is going to be trigonal pyramidal. Or just pyramidal. The tetrahedral, okay, so, okay, and then it's going to be bent if you have two lone pairs. Okay. I think these two things just basically mean the same thing. So now that we have steric number 2, steric number 3, steric number 4 with all the corresponding lone pairs that these things can have. So if you have a steric number 5, and you have 0 lone, hold up. So steric number 5, I'm just gonna read this out and make sure that it makes sense. Steric number 5, trigonal bipyramidal electron pairs. There are 2 axial positions and 3 equatorial. Each axial has 1 repulsion that is at 180 degrees and 3 repulsions at 90 degrees. Okay. Oh, okay, yeah, I understand. Each equatorial has 2 repulsions at 90 degrees and 2 at 120 degrees, each equatorial. The lone pairs go on equatorial positions to minimize repulsion. Okay. So the general shape of this molecule kind of looks like how we had, so when we had like steric number 5 and just electron pair geometry, I think. If I can find it, hold on. Trigonal bipyramidal. Oh, okay, yeah. So steric number 4, with 1 lone pair, you can have trigonal pyramidal, but with steric number 5 and 0 lone pairs, you're going to have trigonal bipyramidal. So you have like the 2 pyramids stacked on top of each other. And so how this is going to look like is kind of like that, right? So you have like this plane, and then you have an axis. So this is called the equatorial, and this is called the axial position. So then there are 2 axial positions and 3 equatorial. And so you have 1, 2, 3. This is a central atom, and it's just going to basically look like that. So when you draw out like each electron density to another, it's going to kind of look like that bipyramidal thing, right? Right? So like it looks a little complicated now that I've drawn like the little lines in, but the basic idea is that when you have I'll put it back into perspective. So when you have a plane and an axis, right? And this is your central atom. And there are 3 here, 1, 2 here. And so the basic thing that, well, like what I read on the slide is just basically saying that when you have this one atom on the axial position, it has 1 repulsion or 1 other thing that's kind of like that it can, let's just A, B, C, D, E, F. Okay. So A is going to feel the forces of all, B B, C, D, E, F, okay? But disregarding the central atom, because that's just basically what everything is just kind of buzzing around, A is at the axial position, and at the axial position, it is going to be able to feel the force of E at 180 degrees, right? It's like completely 180 degrees, like, positioned from, like, in relation to E. And then in relation to C, it has like a 90-degree angle here, and in relation to D, in relation to B, same thing. It has 3 repulsions at 90 degrees. And then each little like atom on the equator, like the equatorial positioned ones, so that's B, C, and D, these are gonna have repulsion, like 2 repulsions at 90 degrees. So again, like B or A in respect to B is gonna be 90 degrees. Like there's gonna be a 90-degree angle between them in relation to also the central atom. And it's also, B is gonna have a repulsion from C and from D at 120 degrees, right? Because this whole circle, this whole plane has a 360 a total angle value, and so when you have it split into 3 different angles, 360 divided by 3 is 120, and so B, D, and B, C, C, D, they all have relative angles of 120 degrees. So moving on, lone pairs go on equatorial positions to minimize repulsion. And so let's say that we have something that's like, that has a central atom, and then it has 1, 2, 3, 4 other things onto it, and then it has a lone pair. So that lone pair is gonna go, like, instead of having like this atom, it's gonna have like a lone pair on the side like that. Yeah. That's basically all it's saying. It's because if you have the, okay. So if you have a lone pair here, what's gonna happen? So we know that lone pairs have a greater repulsion force than any bonding electrons. And so when you have 2, like a lone pair here, and then you have this C and this D, these 2 are gonna like squish together, and A and E are gonna be like minimally affected. And so like really what this lone pair is doing is just like affecting C and D, I think, I'm not quite sure. But it's like minimalizing the amount that like everything else has to change. And so like how this is different from replacing an axial positioned atom with a lone pair is that if you have a lone pair here instead of this atom, I think what will happen is actually like you're making all 3 of these B, C, and D move down. And so E doesn't like that. And you're gonna have to make B, C, and D all move. Like it's like, you have to, I think that would actually be at a higher state of energy, like potential energy, than the one that I had before where like you have your lone pair on the equator. And so basically what this slide is saying is that lone pairs go on the equatorial positions to minimize repulsion, therefore minimizing like the amount of potential energy that this whole molecule possesses. Okay. So now that we know the general like format of this molecule, if you have 1 lone pair and you have a seesaw shape, if you have 2 lone pairs, you're gonna have a distorted T. And I'll like draw all these out for you. Just like, hold on, I'll get there. 3 lone pairs is linear. So as we saw before, when you have like I'm just gonna draw this out again. So we have our equatorial plane, and then we have central atom, axis, like an atom on each side. So if we have a lone pair, right, and we already established that all these lone pairs are going to go on the equatorial positions first. It's not going to like bother with the axial position because that would take way too much energy for them in relation to if they went to this plane part. So atom, 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 and atom. So if you have one lone pair, we know that it's going to replace this first, right? So I don't know, that's weird. Just put X's. So if you have something like this, then the molecule is going to look something like that, right? And so that's going to be a seesaw shape. Because like if you turn it around, it looks like that, right? Which is kind of like a seesaw. So it's called seesaw. And let's say that you have two lone pairs instead. If you have two lone pairs, then what's going to happen is you have a molecule that looks more like maybe it'll be easier if I just. So two lone pairs, these are going to push on everything else. And so what you're going to end up getting is the central atom, this one atom that's coming off of it, and then the other axial positioned ones are going to, I'm like exaggerating a whole lot here. It's like actually a lot less distorted. But nevertheless, it's going to be distorted because these two are pushing on everything else, and so in relation to the central atom, it's going to be kind of scrunched this way. So it's going to be a distorted T, and that's what it's talking about. And then let's say that we replace all of these lone pairs on the equatorial plane with, or all of these atoms on the equatorial plane with lone pairs. So then all of these are all at 120 degrees from each other. They're like canceling each other out. And so no force is specifically pushing towards one way or another. And so in relation to the central atom and the axial atoms, axial repulsions, it's going to be pretty even. And so it's not going to like crush anything towards one side or make anything like flop around. It's going to just pretty much stabilize this, and it's going to be just linear. The molecule is going to be linear because all of these pretty much like cancel each other out. Yeah. So last stirred number, I think. Yeah, stirred number of 6. Everything is just falling in my hands today. Okay. So let's say that we have, I'm just going to check that I have enough space. Yeah, I guess I could deal with that. All right. So steric number of 6. And it says octahedral electron pairs. And so if you have no lone pairs, you're going to have octahedral. Again, just like when we had just the electron pair geometry, we're going to just have octahedral. And then if we have one lone pair, it's going to be square, here in the middle, And 2 lone pairs is gonna be square planar. So this, again, the molecular geometries are pretty much based on the electron pair geometry, just like when we took the steric number of 5, looked at the trigonal bipyramidal, and then replaced each like little atom with a lone pair and saw how that like repulsed everything else. The same concept is going on for the steric number of 6, in that I think actually here, I'll just like dry it out and see if I can make sense of it. So everything is at a 90-degree angle from what I remember. So it's central atom plane, and like there are these like pyramids here, but I don't want to draw that in because it'll look really, really disgusting, and I won't be able to like point out things in the diagram because it'll look just odd. Anyway, so if you have octahedral or no lone pairs, you're gonna have 90 degrees between each of these electron densities. So 90 degrees, 90 degrees, 90, and then from the axial and the planar, that's also going to be a 90-degree angle here. And then if you have one lone pair, apparently you're going to have a square pyramidal. I'm not really quite sure how that works because, So if you replace this bottom electron density due to a bond with an electron density due to lone pair, then wouldn't it repulse a little more than anything else? Why is it still square pyramidal? One, two, three, four. Well, I guess it is what it is. I think it's like generally speaking, it's square pyramidal, but if we were to be like nitpicky about it, then it would be squished together. I'm not really quite sure. I'll have to ask about that one. But like, just know that it is square pyramidal. This really irks me now. Okay. So if you have 2 lone pairs, then it's going to be square planar because you're getting rid of this, and then you're only looking at, you're replacing it with lone pairs. 2 lone pairs, square planar, because you just have a square in a plane for this molecule. Okay. All right. Guess it is what it is. All right, so moving on to polarity. I kind of want to, okay, so there's like this example in my slides, and I kind of want to do it, but I kind of don't because it looks really disgusting, which probably means that I actually should do it. So I guess I'll do it. It's like a big molecule. It's not like one of these simple ones that we've been looking at, but rather like what is like this carbon backbone gonna look like in relation to everything else? I remember doing this with the TA, but I think he said that we don't need to know it in that in depth. Maybe. I just like also realized that I'm like relearning this as I go, and so I don't remember how to do this. Well, a lot of this, which you know isn't really an excuse, but you know, just in case I make a mistake, I'll try to correct it. But please feel free to correct me in the comments below, because I'm not quite sure of if like exactly what I'm doing is right. And so I'm tired. I'm gonna erase that later. So it says fill in the rest of the Lewis diagram and predict the bond angles around each of the 3 atoms designated with an arrow and ethanoic acid. Okay, cool. All right, so let's go. You have a backbone like this. And you're supposed to be able to predict the bond angles around each one. So I guess I'll be looking at 3 different cases. From what I can tell, there are like 3 different, three different simple atoms here. And I think it's gonna be this carbon, and this oxygen. And so this carbon has all 4 of the bonds that it wants. This has all 4 of the bonds that it wants. Hydrogens, 1 bond, are fine. The oxygens, I think, will require lone pairs. Oxygen wants to have 8 valence electrons, and so I'm just gonna give it to them. And I am right. Okay, cool. So then when we have so around this carbon, it's going to be 4 different, steric number 4 for this carbon, yes? Steric number 4, no lone pairs, this is tetrahedral. And I think tetrahedral was the one with the tripod shape. And so the one with the tripod shape was 109.5, was that the one? This is why you need this information on your cheat sheet, because otherwise if you don't remember, then you're not okay for the test. Yes, it's 109.5, thank God, cool. So it'll have 109.5, 5. Cool. This carbon has 1, 2, 3. Steric number 3, therefore trigonal planar. Yes, because there are no lone pairs on it either. And so let's look at oxygen. Wait, trigonal planar. And therefore 120 degrees. Here, here, and here. Oxygen has a steric number of 4, and since it is in this kind of lone pair, this is going to be bent. Steric number 4, but 2 lone pairs is bent. Steric number 4, bent if 2 lone pairs. The angle is smaller than the tetrahedral angle of 109.5. And so in this case, you're just going to be able to say, like, this angle is less than 1 and 9.5, because you're recognizing that this bent form of this molecule is derived from the fact that it's like tetrahedral but with lone pairs. And so tetrahedral has angles of 1 and 9.5, and when you have lone pairs, that's not going to be 1 and 9.5, and you're just going to tell them the direction of like whether it's like less or more than 1 and 9.5. Yes. So that was my summary of molecular geometry. The next video will be on polarity. I will see you there.